Hello and welcome to our webinar, Internet of Things in Motion, Analytics and Transportation. Our speaker today is Gerhard Kress, Director of Mobility Data Services at Siemens. I'm Bruce Posner, Senior Editor at MIT Sloan Management Review, and I'll be your moderator today. Our thanks to Teradata for their sponsorship of this webinar. This event will be recorded and will be available to all attendees approximately 3 to 4 business days after the end of the live event. In addition, today's slides will be available to attendees. We welcome your questions for our speaker today. To submit questions, please enter them in the chat box in the lower left-hand corner of your screen, or you can submit questions on Twitter using the hashtag MITSMR event. If you're having audio difficulties while listening via computer, please call in via telephone instead. Now let's begin. Gerhard, please go ahead.
Thank you very much, Bruce. So today's event is called Internet of Things in Motion, and I want to talk a little bit about how analytics is transforming transportation and what we call mobility, which is everything around trains. When we look at mobility, this is really something that is at the center of our society. When you look at, for example, big cities, you see that everything around bringing people from work to work, having them commute, but also moving large volumes of goods is essential. But it's not only that you have rail cars or metros or trams, but you also have systems that allow passengers to move, but you also have rail automation and signaling that really make sure that there is safety on all those movements. And if you look at all these big cities, especially in Asia, but also the big cities in Europe and the U.S., with some degree of transportation systems, especially rail-based, it would be very hard to have them alive. And what we're doing here in my organization is we provide services to all these operators and try to make sure that they can improve the way they operate and the value of their assets. And for that, we use all the data we get from rail vehicles and from the signaling side. Okay, so when we talk in Siemens about the elements of our strategy, there's really 3 parts: electrification, which is clear, everything around how you use electricity, for example, to move these elements; automation, which is really about making sure you, for example, automate movement of vehicles. But really important, what we're talking about here today, is digitalization. And that means, on one hand side, you have a real asset existing in the world that you connect to a digital network. You do a representation of that asset, or something you call it a digital twin, because you want to understand that asset without needing to touch it all the time. And last but not least, you're supporting those real-world processes with digital workflows. You support them by making sure you understand the behavior of the asset and you feed back into the real process to change something. And let me touch on that a little bit in more detail. What we actually mean is, one of the promises we try to achieve is making sure we get 100% operational availability. This means when you have, for example, a rail vehicle in place, there's a schedule around the vehicle, and you want to make sure that the vehicle is can always be used when the schedule prompts for that. So this means passengers who are waiting for a train are getting the train and are getting the train they want to have. So how you make sure that this happens properly? Well, we take data from those vehicles, and modern rail vehicles are rather talkative. They send a bit over 1 billion data points a year. We're now just connecting a fleet where we're getting up to 4 billion data points per vehicle per year. That is something at least your standard IT structure doesn't usually support. In addition to that, we need more than just those data points. We need things like work orders, so what was broken, what was repaired, which spare parts were used, which spare parts are in stock. Can I actually bring that vehicle to this one depot? Do I have the capacity there to manage that? And of course, it's geographical data, because quite a few of the problems we're seeing relate to certain areas on the network, or they relate to, let's say, geographical conditions like a hill that's causing some strain on the machine and so on. So getting all those things together is not very easy, but it's exactly what we try to do. So we take that data, but the data itself is useless unless we have knowledge to turn it into information. So what does that data point really mean? If I'm measuring, let's say, a temperature on a bearing, and it's 40 degrees centigrade for the Europeans, then what does that mean? Is that something I should react on already, or is it typically normal? That's sort of information that you normally have when you do the engineering or the maintenance of these activities. But even more important is when you have that information, you have to derive an action. Do I need to bring the vehicle now out of circulation, bring it back into the depot to repair it? Can I still wait for a couple of days? What's the most appropriate thing I should do at this moment in time? And that's something where you need, again, a lot of knowledge to turn that information to the most appropriate action that does not disturb the operations. Taking that together, that's really the approach that we take when we use the data and try to make sure that availability is really high. This is also the promise we give to our customers, and we're doing that in quite a few customer projects. In the moment, we have, I think, 15 projects going on in parallel where we really try to aim at 100% availability, and you're going to see at the end in these examples, we're getting quite often quite close to that already. Now, of course, IoT is a word that's being used a lot, and the question is, how do you establish such a capability and a list capability in an organization? The way we proceeded was actually in three different phases, I would call it. I tried to put it here on the slide a little bit. We had the first moves when we started a while ago. We had issues in a certain project. We saw some gearboxes were failing more often than they should have. So we started with some simple solutions, took some data, tried to analyze that, used a lot of engineering know-how, and basically standard tooling that was available somewhere, standard databases, nothing very special. But we already proved there is a value in there, and you can really change the way these vehicles in that country were operating. That was sort of the first proof that there is value in data. I think that should be clear by now for most industrial players that there is a value in data. Then the next phase can really, okay, how do we make sure that we understand exactly what's the business case behind all these topics? What type of investment can we really do? How would we monetize these insights? So we started a phase that I would call exploration. We started with the first set of analytics talent, so a few people that we were hiring, and we were lucky enough that at Siemens, at our corporate research organization, there was a data lab. Basically, it was a Teradata UDA system that we could use, and we could throw all the data that we had in there, didn't need to bother about volume or any other restrictions in that, and spend a little bit of time trying to understand what insights can we get from that data. Because one of the issues that I have discovered in many organizations in the past is there's a great idea about data and its value, but you need to prove it, and the first initial investment is usually relatively high, so the first business case doesn't work out. Then there's a lot of time spent on setting up an infrastructure, hiring some people, but mostly on the infrastructure side, and then if the first thing doesn't work out because there's not enough value in that data, everybody is getting frustrated, and usually efforts are stopped and somebody else needs to restart them. So in our case, I think we used that lab that existed. We took a whole bunch of data from different maintenance projects in there. Some of those did not have enough value in the data for those things we wanted to do. Some worked out pretty fine, and it was then very fast to find a couple of use cases and a couple of business cases that really worked. So the third step that we then took was implementing that in a full-scale fashion. So we ramped up the data services team, and by now we're about 30 people in that team purely focused on data analytics and data services. We also set up an operational platform that is now in 24/7 operation, and we're starting building more analytics capabilities, basically building blocks, analytical models, own developed algorithms, just to make sure that we can now deliver services to our customers that we can really deliver properly as we should do on an operational basis. And I've seen a similar movement with a couple of other companies that I was looking at. exploring first, trying to get a feel, and then investing with the most promising use cases in there. So how does that look like for us in the moment, or at this point in time? We have two pillars that really are supporting our data services. On one hand side, we have a rather large team. You see here a picture. The picture is not fully up to date. We have a few more people now, but you can see it's a rather large group of people, mostly very young people, data scientists, quite a few of them having a PhD in machine learning. They come from various backgrounds. Quite a few of them have been engineers and trained themselves into machine learning topics. Some of them are physicists. Some of them are classical machine learners. I even have a person from finance mathematics in there who's designing models. But we also have some technical experts on these technological topics that we rely on. And we have a couple of project managers who help implement those capabilities with customers, because there's no point in developing something if nobody can use that and you cannot monetize that. The other pillar on which relies is our analytic platform that's in operation now since almost a year, actually 9 months in full operations, and that is based on a very scalable storage because their volumes are rather large. I'm getting easily from one fleet of trains, let's say 100 trains, a few 10 terabytes a year. So my data volumes are somewhere in the range of 100 terabytes, and that's nothing you can just manage in a standard, ordinary, classical single node IT structure. So we use, as you can see on the picture on the right-hand side, we use a Teradata system for the database. We use a Hadoop cluster for many of the non-structured, unstructured data elements, and also for archiving colder data. One of the challenges we were facing in the beginning is that when we're storing all the data, we need to bring the analytics into that database. So it's easier to move a program, software, into the database than it is actually to move the data out of the database, extract it, process it somewhere else, and write it back. Because, as I said before, it could be that I'm talking about 20, 30 terabytes of data for one type of rail vehicles that I need to analyze over a large period of time. One element that we also had to incorporate in our platform is really data quality validations, and that's important because we're getting sensor data from hundreds and thousands of sensors out in the field. They're in these vehicles. Those vehicles vibrate, and that is not necessarily a good combination with sensors. So we see also sensors failing occasionally, and we have to be very careful not to take false sensor data and then derive alerts from that and take vehicles out of operation or alert our customer for something very urgent, and then it turns out that it's simply a false alarm because we got the wrong type of information. Next to that picture on the right-hand side, you see a little bit of a sketch of how our platform looks like. It's a very classical IT stack. We have data sources. We transfer data on something where you can plug a cable into. We have to integrate the data, and the challenge we're facing here is that there are train vehicles run rather for a long period of time, so lifetimes are between 30 and 40 years officially. Some of them run a bit longer. This means that I have to deal with all type of data structures that were standard and state-of-the-art maybe 10, 12, 15 years ago. And if you think back in your history, how IT looked 15 years ago, that's nowhere close to what we have right now. So I have to support all these structures, and I probably have to support them for another 10, 15 years still. So then master data is really the thing that helps us make our data readable. And then we have two ways how we deal with data. The left part of this diagram shows what we call operational analytics. We basically provide the data to our customer, either what the vehicle knows already about itself, they all have a self-diagnostic system, or we provide additional information with analytics from the data that the vehicle does not yet know. For example, we make a prediction about the failure of a gearbox or of a door or a bearing, something like that. So we predict this door is going to fail in the next week. The most appropriate time to exchange it would be in 3-4 days, because that's the best relationship between risk and reducing your cost level. That's what we call operational analytics, because that you can use for the dispatcher that's making sure to manage the fleet out in the field, or you can use it for somebody who is dispatching the activities in the maintenance depot. But the big challenge is to get to these analytical models that exist there, and therefore we have the right-hand side, which is what we call data discovery. That's our data warehouse that stores the lifetime data of every vehicle where we can get data from. And then we have our data mining workbench on top, where data scientists are trying to find patterns. And I'm going to talk a little bit more about how to do that a bit later. So that's sort of the setup we have. Now, of course, the question is, what are the value levers that we really provide to our customers? What are our customers really paying for? And basically, so before, it's improving availability. That's really a key lever. And the other thing is, of course, making sure there's no surprise in the operations. If a vehicle is out there on a journey scheduled and transporting passengers or goods, you want to make sure it arrives properly in time, as scheduled, and does not break down somewhere. You don't have problems where you need to reorganize your schedule. So there's 4 value levers that we really address. The very first one is very simple: improved maintenance, making sure that the maintenance people know before the vehicle arrives what's going to happen, what resources they need, what type of spares they need, and have that prepared. So that's simply making sure they can do a better job. Second thing is, and that's already quite relevant with data, is root cause analysis. So we have complex problems that appear, and we need to find out where they're coming from. For example, there is, especially in Europe and in Asia, but also now in the US, there's these train safety systems that make sure that signaling transmits information to the vehicle, and if there's signal putting up on red, you basically have to stop the vehicle in front of the signal, making sure you're not having any safety problems, you're not bumping into other trains, or so on. The majority of these problems we see with these systems is not coming from the component on the train, but it's coming from the interaction with the environment. And that could be that there is snowfall that creates problems for some of the radars involved, or there is equipment on the tracks that needs to communicate with the train that starts fading. There might be more of those points. Data can help you to make sure that we understand that issue a lot earlier and can solve it rather fast. The third point is really reducing preventive maintenance costs, because in the rail industry, you have most of the time a very elaborated preventive maintenance schedule. You want to make sure you exchange components before they wear out and before they break down. However, the problem is that we see very often these components are exchanged prematurely. People, for example, take mileage as one of the single most important elements in there. But for example, there's compressors on the locomotive that provide air pressure for the brakes, and they don't really understand how often that system is being used. So they exchange that component maybe way too early. Or brake pads, which is one of the core elements as well that provides a lot of cost. We see it very often being exchanged 20-30%, when still 20-30% of remaining useful life is there. So what we're providing is analytical models that tell you what the remaining useful life of the component still is, and what is the best time period to exchange that causes least disturbance to your operations and still gives you the best cost position. And last but not least, the last line is predictive maintenance. The core element of predictive maintenance really is to make sure you don't have a failure of vehicle somewhere on a journey, but you understand the upcoming problem before, and you can replace that component at the time when it suits you best. So, for example, for high-speed trains that we have running in Europe, I can predict the failure of a gearbox a week, sometimes 10 days in advance. And so you can do that, replace that component at a normal depot visit somewhere at night when there's no passengers on the train, when the train is not scheduled to operate, somewhere between 2 and 5 in the morning. And there's no disturbance. Nobody's going to see that there's any train really missing out there. And so that is one of the key drivers to increase availability. Just as a side remark, what we see a lot across the world is that a lot of operators up to 10-15% spare capacity in their vehicle fleets, because they want to make sure that if there is a breakdown of a vehicle, an accident or something else, they have enough capacity to continue their operations. If you use data in this way and you can really do all the predictions, then it's possible to operate the same network with much, much less spare capacity. We actually have one customer, and you're going to see that later in our list, in Bangkok, who is running the system with no spare capacity in their peak hours. Okay, they have a slightly better system because there is this elevated train system, so they don't have any accidents with cars or passengers, but still you can massively reduce your investment, or with the same fleet you can provide a much better service, basically at almost no extra cost. So this is a very important element that we try to provide to our customers, and that really is very valuable to them. I said before that we built this team, and we need a lot of knowledge from the data and understand what that data really means and what's the best appropriate action. And the reason for that is that, oops, that was too fast. The reason for that is what we're doing here is we're looking for rare events. It is not that a component on a train breaks down every day or every second day. What actually happens is the gearbox, for example, on a high-speed train will have a problem every 3, 4, 5 years. So the majority of the time, the data is extremely boring. But we need to make sure that we pick up exactly that moment when there is a problem appearing, the gearbox is still fully functioning, but is bound to break down because there is a problem in it already, and picking out exactly that phase shift between the fully functioning gearbox to the one that has to break down and will break down in due course. On a high-speed train, that's somewhere between 2 weeks, maybe 3 weeks, depending how early we pick this up. So the way we approach that is we take the data and we use on one hand side data mining, machine learning techniques. So we have a couple of algorithms. We've developed own algorithms that we're trying to patent, and very interesting ways how we combine data from different parts of the vehicle to make or help us make even better algorithms. The other part that we also use as part of the model is engineering knowledge that is provided by our engineers. It's expertise from the system design, from the way how the systems were developed, and also we use simulation results from our engineers a lot because we need to have them as boundary conditions for the model. When we're trying to predict very rare failure events, the biggest challenge we face is avoiding what we call false positives, false alarms. If I have a problem in a gearbox every 4 to 5 years on a vehicle, maybe 6 years, then it's very hard to figure out exactly this one point every 4 or 5 years when the gearbox has a problem. So if I have too many alarms and I pull out the vehicle, exchange that gearbox, spend hours of work time and very expensive spare parts, and then it turns out that gearbox was still fully okay, there was no problem, then our customers would not be happy because they would drive up their costs but would not help them at all. So preventing these false alarms is one of our key issues there that we're striving for. And the only way we found to do that, on top of what the data already can deliver, is putting additional information into those models that help us to make those models even better. So that is the part why it's also very important for us, our team. We sit in a locomotive factory. We are exactly between the production facility and the engineering building. So we have access to all the information that is available. We've learned to ask in the language of the engineering. And it was the biggest challenge I had in my team, getting all these great data scientists who are brilliant mathematicians, getting them to understand what an engineer says when they talk about all these nice components, how a brake pad looks like, how the abrasion really happens there, and having them communicate, because we need that information to make sure that we provide the right insight. And that's exactly what we provide to our customers. And what here is the validated action proposal. But basically what we do is we tell our customer, you have this and this issue coming up. That's what you should be doing. Those components you have to change. On those components you need to check. And that's exactly what we sell and provide. So it's not just we raise an alert, send a message, problem with the gearbox, but do a lot more and actually try to help them and guide them through that process. So now, of course, the question is, how does that work? How does that really create a value for our customers? And here, a couple of examples. These are the examples I can, in a moment, name. But as I said before, we have 15 projects going on right now. For some of them, unfortunately, I cannot yet disclose the customers. But one of the first ones we did was the high-speed train in Spain, which has an availability that's pretty close to 100%, 99.98%. And basically, it was delayed once on 2,300 travels between Madrid and Barcelona. And the very interesting part here is when those trains started a couple of years ago, Renfe, the Spanish rail operator, was trying to compete with the plane on that journey. The plane takes an hour and a bit. The train takes, if it's direct without stops, it's 2.5 hours. And 80% of the people were actually taking the plane at that time. And now, just 2 months ago, those numbers have reversed. So now 80% of the passengers traveling from Madrid to Barcelona or back are taking the train, and only 20% are still on the plane. And that is because those trains are punctual. And actually, Renfe even reimburses passengers with the fare if the train is delayed more than 15 minutes. So that is great, and this really has helped Renfe to operate a very profitable, very, very good service. The other one I said really about Metro Bangkok is these are metros on one side, and the SkyTrain there as well. And the clear target is 100% of the vehicles need to be available in rush hours, and rush hours are defined rather broadly. So it's almost half the day is rush hour. But basically, they operate without any reserved trains. And those metros are running at such short cycles that if you have a problem with the door or a train starts failing, you actually disturb the whole operation for the day, and that would create quite some chaos in the public transport. And even their availability is also very close to 100%. One of our flagship projects is another high-speed train, Belarus, Russia. That train started between Moscow and St. Petersburg with only 8 trains, and if you only have 8 trains, you basically have no spare capacity. And this was also really the first high-speed train in the country, but now there's 16 trains operating, and availability is also very close to 100%, and it's one of the most successful ventures that RGD, the Russian rail operator, is having in Russia. And now we're building the commuter trains as well and operating them because they believe that success can be replicated. And last but not least, Eurostar, which is a train we're now just delivering to travel between London and Paris and back. Just the first trains out. That's why I don't have availability numbers, because the first 4 train sets are just in the moment in operation, and they're still in the introduction phase. But actually what we're doing there is we're monitoring a couple of components. In that case, we're still under warranty from Siemens, and making sure that there is, on one hand side, vehicle problems, and some of them appear in the warranty period, are picked up before they manifest themselves so the passengers can see them. And the other hand side, we also still see that there's issues when some drivers are not yet used to the new technology, and we see some improvement possibilities or training possibilities. So basically, we're safeguarding the start of those new trains, and hopefully in a few months we can show you some very high availability numbers here as well. So that basically is showing you what you can do with that data and how the journey was that we started here. And I would now like to go to the Q&A part.
Okay. Well, thank you, Gerhard. That was very interesting. I wanted to welcome questions, and we've been receiving many questions, a lot of good questions, and we'll continue to take questions for the next half hour or so. You can submit your questions by entering them in the chat box on the lower left corner of the screen, or on Twitter using the hashtag MIT SMR The first question, someone asked, and this is very, on one of the slides you talked about MPP, and the question was very simply, what does that stand for?
Yeah, sorry. MPP means massive parallel computing, massive parallel processing, actually. And what that means is, in the traditional paradigm of IT, you have a database and you have a server serving exactly the full database, and that's where all the data resides. If your data volumes grow tremendously, that server becomes a bottleneck, and in the end, your performance of the system goes down. So that standard database cannot hold unlimited volume of data. If you want to scale unlimited, what you need to do is you need to take that database and chunk it or rip it into small chunks that all have their own processing power and small storage, and these are what you would call nodes. If you build them properly, these nodes don't share anything among them. So if you want to grow your data storage capability, you simply put more nodes next to them. And Teradata is one of those systems that exactly does that. If you need a double capacity, you simply add more nodes, and the system will be up and running immediately again. So that is the type of system we need to use if we want to scale to very large volumes of data. I mean, in the big data world with a bit over 100 terabytes, we are not the biggest one, for sure not, but we're sharing the same infrastructure with some other Siemens entities. So overall, we're getting close to the petabyte range, and then it starts really getting interesting. And the only way you can store and process data in that or in that magnitude is when you use a fully parallelized system that does not share anything among the different nodes, but a request comes in, is moved to all these nodes in parallel, processed there, and you get the answer back. And that's exactly what MPP stands for, and basically Teradata is one of the systems. Also, when you look at Hadoop, it's also an MPP-type system because you have nodes that help you scale the system. And basically the only thing that limits your scalability is the place you have and the budget for hardware.
Okay. Another good question is, how did these capabilities change your business model? Are there sales relevant factors or add-on packages, or do you even stop selling vehicles and sell vehicle availability?
It changed the model quite a bit. We're still not at the point where we stop selling vehicles because there's still a large demand for customers who want to buy the asset and own the asset and operate the asset. And the majority of the maintenance activities in the rail business is done by the operator, simply because most of those are state-owned railways. They've existed since 150 years, whatever, since the beginning of the rail period. And they have a tremendous amount of knowledge in maintenance and making those things run properly. What we provide is an additional value add to them because there's a lot of information that we have around the engineering of those vehicles, so we can interpret the data in a better way. I can take data from different fleets and generate a better insight than if I only have a smaller fleet with one customer. But the business model really has changed. That in the past we sold vehicles and we sold maintenance more or less at a rate per kilometer. Now we sell availability if the customer wants that, and basically help them improve availability. Even so, we are only consulting in some of the ways how to do maintenance, and they run their own process world. But then we discuss with our customers how can we share in the value add that we've created. So moving from a classical effort-based model really to an outcome-based model. That's exactly what's happening right now. And we have quite a few contracts already doing exactly that. So that the business model has changed. Maybe in the future there will be more demand for something like, I would call it, mobility by the hour or availability type of systems, but at the moment we don't see that yet taking hold in the market.
Okay. Another question that came in is, to what extent are the 4 key values that you mentioned appreciated by potential customers? And I guess that's, can you speak to that?
Well, the value that these value levers that we provide, I mean, they're appreciated by the customers a lot, because the first 3 levers, better informed maintenance, root cause resolution, and optimizing preventive schedules, they really reduce the cost of maintenance. And if the customer does their maintenance, they actually save a lot, and we expect somewhere between, depending on how they do today, between 5 and 12% savings on man hours, material, and so on. The fourth lever, predictive maintenance, is not so huge on the cost side. Well, it makes sure you don't have these emergency actions. You don't have to rescue a vehicle from somewhere, and that can be pretty bad if you're somewhere in the outback in Australia and you have to rescue a train for 1,000 miles from somewhere. But the biggest impact it really has is increasing availability, making more of your asset available to revenue operations. And that part is also very appreciated. So we have quite a few discussions at the moment on how we helping customers increase availability and what they can do with that spare capacity they're getting. Actually, one discussion we have with the European rail operator is they're saying we need to provide more service to our passengers, but at this point in time we can't afford to buy new vehicles and the delivery period is too long. Can you actually help us to get more out of the fleet we already have? And that is something that provides a tremendous upside also on the revenue side for our customers.
Mm-hmm. Someone inquires about whether you see using any of these capabilities in other areas of transportation, and how the different modes will connect. How do you see the other areas of transportation evolving in this area? Another question came in had to do with whether some of these same approaches could be used in bus transportation, given the fact that there are other extraneous factors having to do with traffic and all.
Some of those things can be used as well in other modes of transportation, especially when we talk about road-based traffic. I think the biggest difference in road-based traffic and rail-based traffic is that congestions are a little bit more often on the road and a bit more difficult to predict. On the rail side, usually you have a central signaling system, so you know where on your network which trains are, what their destinations are, and at least you have some pre-warning if there's issues coming up. That's not so easy on the road. But, for example, when you look at truck manufacturers, they're using very similar exercises like what we're doing to make sure that availability is much higher. And, Siemens is not producing trucks, so we're not very active in that field. But some of the technology we're using on electrical motors contains similar approaches as well that we sell into OEMs. But yes, you could do the same thing. You just need to take care a little bit better about predicting the traffic patterns of many more actors on the road, because that is a heavy influencer.
Okay. Here's a question that came in having to do with the format of the data. How necessary and how intensive is the retrofit for the data communication to make it useful for analytics?
Retrofit in my world means we are deploying deploying connectivity options into all the vehicles. That is extremely important because there's a time, I would say, vehicles delivered 6-8 years ago, and prior to that, they don't really have a lot of connectivity embedded because the time was still expensive. Remember all the time when we had these huge bulky phones. We had in Europe GSM connectivity, so the bandwidth was basically not helpful. And when you move those things to higher speed, the bandwidth doesn't get better. It simply degrades to a level when you cannot transmit a lot. So the older vehicles usually did not have a decent connectivity system. So we are retrofitting a lot on the installed base because there's still a lot of data gathered, and we need to bring that data to the land side and process it there. The biggest challenge we really have is the different data formats and the different semantics that are put to that data, because all the changes in IT technology allowed us now to do things a lot easier, but we couldn't do that 10 years ago. Today I'm getting either XML files or JSON files. I'm getting semantics embedded in the file, something that you never had 10 years ago. You had some very interesting bit level compression in there that makes it quite difficult to read. So this is my biggest problem. But in the rail sector, it's hard to change that in a retrofit scenario, because in most countries in the world, you have to get what's called homologization. Basically, you have to get an approval from the authorities that this vehicle with that software on the vehicle is safe to operate. And if you change the control layer on the vehicle, the control units that control braking systems or the drivetrain or the doors, whatever, you immediately have to go through a recertification, and that is usually quite expensive. So we try as much as possible not to change those systems, because that is usually a nightmare.
Okay. Someone asks, and this is kind of a basic structural question, does the customer have to set up its own IT infrastructure, or do you provide those IT services?
We provide that to our customer. Basically, we provide this platform that I showed before in this small diagram. They can access them through the web. We are hosting that. It's on Siemens-owned hardware, and they can connect to that, so they see where the vehicles are. They get the information, the status. They get the predictions and all those things. However, a lot of our customers are rather large ones, so they have their own enterprise IT systems, and we do a lot to integrate with them as well. So we either transfer the information directly into their systems. So, for example, in a work order management system that they have, we provide the work orders there directly, or we provide data in raw format or in readable format into their systems, depending a little bit on what the customer needs. But we try to provide it as a hosted system, a hosted solution with an own UI to make things a lot easier. On the analytical part, the data warehouse, we are centralizing that as much as possible, because my key concern there is I have to be able to scale with very large volumes of data. I have to be able to absorb it at a high speed, and I have to be able to do that while my data scientists are running models and training analytical models. And that is a tremendous amount of processing power that we need to develop these models. So in the picture you've seen before, that cabinet on the left-hand side with our database, and that contains over 100 CPU cores, simply there to train the models. And if my guys start working, we can keep those things busy for hours. So that is something where most of our customers do not have the infrastructure that could handle such dramatic workloads in their own system. That's why I'm trying to do it centrally, simply because I can make sure it works in scales and it doesn't break down if my guys start training models.
Okay. A couple of the attendees have commented on your high availability numbers and your performance numbers, and they're quite impressed with those numbers. The question that one person asks is, how much of the improvement is due to IoT sensors and data, and how much is due to the process refinements? And let me add another question to that at the same time, and that is, and maybe you can deal with them at the same time, how to what extent have you looked at geological data and weather data that could influence repair and breakdown issues?
Let me take the second part first. Weather data and geodata is extremely important. Weather data, for example, you have snow coming in, then one of the classical things that happen, you have these doors, there's a sliding step going out. If it gets too cold, it starts, it's more difficult to move. So if the motor is already a little bit damaged, then you're going to get a problem out earlier. Those type of things are totally common, and the pattern of problems we see between, for example, winter and summer is very, very different. When you look at the Velara in Russia, in winter when it's really cold, between Moscow and St. Petersburg, that train gains over 1 ton of extra weight because there is water freezing on the train, and it simply is being carried into the end station. So that creates a very different behavior of that vehicle. So it's extremely helpful to have a good weather forecast, and not only from start and end station, but also what's happening on your way. With regards to these availability numbers, I know they're extremely high, and we always get challenged that they're really correct. And yes, we've been able to prove that over and over again that they're correct, but they are availability to schedule, so to schedule the operation of the vehicle. It's very hard to differentiate how much of that is coming from use of data and from good processes. And it's both. It's not only data, because if your processes don't allow you to properly deal with a prediction, then the prediction doesn't help. We have customers where we said, we're not going to give you predictive maintenance because you can't use the information. We're first working with you on making sure your processes get more stable. But a lot of that is data, because the earlier you know that the problem is appearing, the better you and more easy you can deal with that. For example, on these trains in Spain, if you only have 4 tracks or so in your depot, you cannot repair more than 4 trains at the same time. So you need to make sure that you have enough pre-warning time to arrange your capacities and the people in a way that you can execute those activities properly. Or if there's a component we need a very specific skill, and there are some of these components on the train where very few people are trained on them, you need to make sure that you get your shifts rearranged in such a way that the right person is there when you need that person with that skill. So it's a mix of both. And yes, we do things also different in the maintenance processes. That is true. But we also use data. So I couldn't say or tell you how that would be if we would not use any data, what availability would reach. It's very hard to say. We would probably need a lot more people to stay on a level the customer would still accept, I would guess.
Somebody had a follow-up question regarding the IT system and the IT services, and the question was, how global is your cloud computing service?
It's as global as we can do it on legal reasons. So basically we're offering at the moment in Europe and the US and parts of Asia. There are certain areas in the world we're not allowed to take data from rail vehicles out of the country. In those countries we cannot offer that, but there's very few of them, and so I would say it's global.
Okay.
So in the moment I have customers on it from the US, from many different countries in Europe, some parts of the Middle East, Asia, and Australia.
Mm-hmm. Here's a question that, and there have been a few in this on this topic, having to do with security. Where does cyber risk fall into your view, and how do you protect systems and sensors from cyber vulnerabilities?
That's a very, very good and very important question, because we see cyber risk getting more and more important, and we also see that our customers start appreciating our efforts there a lot more. Basically, first of all, on the train side, we make sure that whatever we do, extracting data from there, we cannot write back. that the first thing, so even if our box will be taken over by somebody, you cannot do something bad for the safety of the passengers. That's the most important element. So safety is absolutely crucial. We must not have accidents because somebody could take control of the train. And then we do a lot to safeguard the communication. So, for example, our boxes, they set up a VPN tunnel to a set of systems at Siemens. Of course, it's encrypted. There are certain mechanisms that you cannot play a man-in-the-middle attack. When we designed our system, we did what's called a threat and risk analysis. Basically, what threat scenarios can we imagine? What risks are there? What elements do we need in the architecture to protect ourselves from that before we started developing anything? So just because when you have a security in the architecture, it's so much better than if you start coding it later, because you always have some loopholes left. Then we built the whole system. We follow the same security standards than the SAP systems that are operated by Siemens. And that, for example, includes that we have every few months penetration tests and also friendly hacking into our system, because I rather like to know myself that we have a problem and can fix it. Then if somebody else shows me the problem and some data is stolen and brought to somewhere. And we also try to protect ourselves from if somebody is tampering with the data, that could be possible sometimes. So we're looking at, is that data plausible? Are we triggering reactions that we shouldn't trigger and that are strange or uncommon to that type of weight? So we're looking at those scenarios as well to make sure we pick up these elements as well, and then have a manual check on how does that work.
Second question that came in regarding data, and that is, in your contracts with your customers in terms of data sharing, do you require that certain data be shared in order for you to deliver the availability? And is there any data that is considered too sensitive to share?
First of all, our clear position is the customer has bought these assets, so the data belongs to our customer. And what we ask from the customer is to get usage right, because without using the data, it's very hard to do analytics. And depending on how much risk takeover we're supposed to be having, we need more and more integration into the customer's processes. So if we're supposed to guarantee for availability, we need to understand something about the work orders. We need to have a feedback loop and so on. There's certain information we're not sharing. It's everything that is person-related information. For example, driver names, the names of the people who have been executing maintenance, those type of things we don't need. There's no value for us in that data. And there's data we don't want to have in there, because then you get in all these privacy law topics that is very, very hard to deal with in a sensible manner. So, yes, we have a list of data that we need to have from our customers if we provide that service. But it stays their data, and whatever we do with that, we're very open and share that with our customers. And we are only using the data we absolutely need to provide that service.
Okay. Here's a question that came in from someone in a different industry, and this is the question is, have you and your team been involved in extending your learnings and experience to other industries and applications?
Yes, quite a bit actually. On one hand side, of course, the nice part about Siemens is we have all these different industries we're supporting. So the platform on which we reside, for example, is shared across different parts. It's for gas turbines, wind turbines, healthcare equipment, and so on. It's being used by different parts. And we share also the analytical models. So some of the thing when we sell gearboxes to mine crushers, for example, they could use a similar algorithm that we're using on high-speed trains. That's one thing. But also we're sharing with some of our partners in different industries some in the airline industry, we're working with some companies where we're doing, let's say, co-innovation, and we're also doing hackathons together, or in the automotive industry where we are not really as seen as a big player. So we're doing that as well. And we are doing quite an effort to work with innovative young small companies, startups, or slightly older startup companies, and share information back and forth, because we believe that innovation is not something that happens only in a corporate environment or in a large company, but there's so much innovation out there, and there's a lot of win-win scenarios we can play out there. But these are very individual settings. There's not one value proposition I could give you that works for every startup.
Okay. There have been a couple of questions involving pricing, and one was a general question, how are some of these services priced? And a more recent question that came in had to do with a different approach to pricing based on performance. Are you able to offer services based on results, value billing, or revenue assurance based on your IoT capabilities? So I guess this would be, are there ways to structure the pricing to reflect the value?
Absolutely. We do that, and our customers are very, very clear about that. This is not a flat fee engagement. You pay us this much, but very often, most it starts that we do a pilot to prove the value, then we try to align on what's the value baseline and what value are we creating and what share of the value are we getting. And obviously, the more risk we're taking, the higher the share we want to have. But that is a classical value-based selling approach. What we do not do is we're not taking customer revenue risk. For example, when many of our customers are train operators that transport passengers, we're not going into risk of selling tickets because there's not a lot we can do about it. We can help them provide a good service. We can help them to have available trains, and that the technical parts for punctuality are there, but we cannot run the operations for them. We would never do that. But yes, we do value-based pricing models. Anything else would not work in this case.
Mm-hmm. A recent question that came in has to do with how you can use the Internet of Things, and this is the question was, what can the Internet of Things do for compliance?
I think the question is, what is meant with compliance in that case? If it's legal compliance, there are a couple of things that can be done when you look, for example, at there's regulations on speed limits or certain things in tracks, especially in areas we don't have a train control system deployed. Yes, this can be done. When you look at compliance for internal procedures, this can also be done. For example, looking at procedures around energy efficient driving or driving that helps you reduce maintenance efforts long term. Those things, yes, this can be done, and for some customers, we're looking into that.
Mm-hmm. We have time for probably one more question, and I guess this one is an interesting one. It has to do with data quality, and the question is, what are the key data quality challenges you have experienced so far?
Oh, there's quite a few of them because we get so much data from so many different sources. When I look at classical IoT data coming from trains, the first thing is we see sensors failing, or we see data being not locked properly for a period of time on the train. So basically, false or wrong data being transmitted, and there's always some stuff in there, or the sensor couldn't really probably agree on a reading and then send the default value. Those type of things we need to pick up. That's what I said before under data quality validations. That's a very important element. When we look at, there's a lot of data also on these vehicles that entered manually when you have a crew on the train that sees certain issues on the train that's not monitored by sensors and enters them manually. We try to provide applications that don't ask for too much free text writing, because that is usually very hard to interpret. And then when we look at work orders in depot, that is really hard to make sure we understand what really happened. So we, for example, cross-correlate very often these work orders with the spare part consumption to make sure that we really understood what was meant. But one of the challenges we have is you cannot have 100% data quality. That's impossible with that large volume of data. What we have, the system we use is we try to validate data and assign sort of credibility ranges to that. That data sounds very credible. That data does not look credible at all, and that one we actually don't know. We're not sure. And that is something that we use as an input into our models. We're not throwing away data, even if we're sure it's very unplausible, probably wrong, because that pattern, how that appears, could tell us something about the way, for example, a sensor is failing, or a software problem on the train that, under certain situations, delivers wrong data. But we basically take something like confidence intervals as a basis into our models and try to make sure that the unreliable data is not distorting our models.
Great. I think that is about all we have time for today. This concludes our program, and thank you again to our sponsor, Teradata. A reminder that a recording of the program and the presentation slides will be available within 3 to 4 business days. Thank you, Gerhard, and thank you all for attending our program today.